Welcome to Scoli Sleep Stories. Before we begin, take a moment to get comfortable, let the day soften around you, and settle in for a calm documentary made for curious minds. If these stories help you rest, learn, or simply enjoy a quieter part of the day, please consider liking this episode and subscribing to the channel. Now, when you are ready, let us begin. Chapter 1. Leaving the Familiar Shore. Evening settles gently over the harbor as the vessel prepares to depart. Along the quay, ropes loosen from worn wooden posts, and the last voices carry softly across the water. Gulls circle above tiled roofs and quiet warehouses. Small waves touch the stone walls with a steady, hollow sound. Beyond the harbor entrance, the sea reflects the fading sky in long bands of blue and silver. A headland stands against the west, darkening as the light withdraws. Farther inland, a tower catches the final glow of day. On board, a lamp has been lit above the chart table. Its flame shifts whenever the ship rolls, laying warm light across inked coastlines, compass roses, and brief handwritten notes. A finger follows the narrow channel leading toward open water. Nearby, someone watches the harbor marks come into line. At the helm, another sailor holds the vessel to its ordered direction. The voyage has begun, though the familiar shore remains close. Before satellites and electronic charts, finding the way across the sea was rarely a matter of trusting one instrument or one calculation. Navigation was a patient practice of gathering and comparing clues. Sailors considered what they could see alongside what they had been taught, what had been written down, and what earlier voyages had revealed. They observed the coast, the compass, the sky, the wind, the sea, and the motion of the vessel itself. No single clue was perfect. Together, the clues could form a dependable understanding. A voyage commonly began with detailed knowledge of the place of departure. Mariners needed to know the shape of the harbor entrance, the positions of rocks and shoals, the depths of the channels, and the direction and strength of the tides. They learned which headland appeared first when approaching from sea, and which tower, hill, tree, or pale cliff could be recognized from a distance. Even before the vessel crossed the harbor mouth, navigation was already underway. Much of this knowledge lived in people. An experienced sailor might teach an apprentice where a current curved around a point, or how the water changed color above a shallow bank. Instructions were repeated over many passages until they became familiar. Some knowledge remained local, refined by generations of mariners who knew one coast exceptionally well. A pilot was a navigator with detailed knowledge of a particular harbor, coast, or waterway. The pilot might board a visiting ship near the entrance and guide it through channels that appeared broad and simple on a chart, yet contained hidden shallows, changing currents, and difficult turns. Such knowledge came from long observation. The pilot knew not merely where the marks stood, but how they appeared through morning haze and evening shadow, at rising tide and falling tide, in calm weather and beneath a low sky. Other knowledge was preserved in writing. Logbooks and journals recorded headings, winds, distances, and observations from earlier voyages. Charts showed coastlines and hazards. Tidal tables helped sailors estimate when the water would rise or fall. Astronomical tables provided information about the expected positions of the sun, moon, planets, and stars. There were also rudders. A rudder was a written set of sailing directions describing routes, hazards, landmarks, and distances. It might guide a vessel from one harbor to another, noting currents, anchorages, and dangers along the way. A rudder could explain that a certain island appeared low when viewed from the east, that a pale cliff marked the safer channel, or that sailors should keep a particular hill in line with a church tower until deep water was reached. These records did not remove uncertainty. Instead, they allowed mariners to meet uncertainty with accumulated experience. The work of navigation was usually shared. Although histories sometimes remember a famous captain or navigator, a ship found its way through the combined attention of many people. The master held overall authority. Pilots contributed local knowledge. Mates supervised the vessel during their assigned hours. Helmsmen steered. Lookouts watched for land, lights, reefs, drifting objects, and changes in the weather. Other crew members measured depth, handled sails, recorded observations, or turned the sand glass that marked the passing of time. Life and work on board were often arranged into watches. A watch was a scheduled period during which part of the crew operated the vessel, while others rested or attended to different duties. As one watch gave way to the next, information passed between them. The new watch needed to know the ordered direction, the wind, the state of the sea, the estimated distance traveled, and anything unusual that had been observed. Navigation continued through careful conversation and record keeping. It belonged to the vessel as a whole, rather than to one solitary figure standing over a chart. Now the departing ship reaches the outer channel. The helmsman keeps the bow aligned with a familiar mark on shore. The direction in which the vessel's bow points is called its heading. Yet heading alone does not reveal exactly where the ship will go. Wind may press against its side. A current may carry the whole vessel east or west, even while the bow points steadily forward. The course through the water is the vessel's path relative to the water surrounding it. The course over the ground is its actual path across Earth. The two may differ. A leaf floating in a river offers a simple comparison. A small boat can point directly toward the opposite bank and move forward through the water, while the current carries both the boat and the surrounding water downstream. The boat's heading remains aimed toward the far bank, but its course over the ground becomes a slanting line. At sea, this difference may be difficult to see. There are no fixed posts standing in the open water, and a current is often invisible. Navigators therefore estimated its effect from experience and observation. Later they compared their estimate with landmarks, soundings, or measurements made from the sun and stars. Position means the vessel's location at a particular time. Today, a receiver may display a precise latitude and longitude almost instantly. Earlier navigators often worked with a well-supported estimate. The ship was believed to be a certain distance from a known headland, along a particular course, after traveling for a measured number of hours. This did not mean that the crew was lost. Once land disappeared, sailors continued estimating position from direction, speed, and elapsed time. They considered the effects of wind and currents. They watched for changes in clouds and water. When the sky permitted, they observed the sun or stars. Each new piece of information might confirm the previous estimate or gently suggest that it should be revised. Navigation was not the art of pretending to possess perfect certainty. It was the discipline of making the best supported estimate available, and then calmly correcting that estimate as new evidence appeared. Some voyages remained close to shore because coastal routes offered visible landmarks, sheltered waters, and regular places to anchor. Yet ancient mariners did not all remain beside coastlines until the time of later European ocean crossings. Ancient and indigenous sailors in many parts of the world made deliberate journeys across open water. They carried knowledge suited to their own seas. They remembered star paths, seasonal winds, ocean swells, the movements of birds, signs of distant islands, and routes taught across generations. Their traditions varied from place to place, but all depended upon skilled observation, memory, judgment, and practice. Even a finely made instrument could not navigate by itself. A compass depended upon correct use and an understanding of its limitations. An observation of a star required clear enough weather and a visible horizon. Tables might contain errors, timekeepers could lose or gain time, charts might be incomplete, and coastlines could be drawn from reports of uneven quality. Records had to be kept carefully, and every observation had to be interpreted with skill. Instruments extended human perception. They did not replace human judgment. Modern satellite navigation belongs to this long history, rather than standing entirely apart from it. The Global Positioning System reached full operational capability in 1995, but mariners had already used radio navigation, radar, and other electronic systems for decades. There was no single leap from the sextant directly to GPS. New systems joined older practices, and prudent sailors continued to compare one source of information with another. A screen may offer coordinates, just as a chart may offer a coastline. Someone must still understand what the information means. Behind the departing vessel, the harbor has grown small. Individual buildings merge into the darkening slope, though the tower remains clear against the last pale band of sky. The pilot studies its position beside the headland. Near the rail, a lookout notices the water changing color as the channel deepens. At the chart table, the lamp continues to glow over the lines of the coast. For a little longer, the shore speaks through shape, shadow, current, depth, and sound. Soon, the last familiar marks will fade beyond the evening sea. Before they do, there is time to notice how much a coast can reveal. There is the curve of a hill, the measured rhythm of surf upon a hidden bank, the paler water above sand, and the quiet knowledge of a local pilot who has read these signs for many years. The tower grows smaller behind the stern. the headland settles into dusk, and as the vessel moves steadily outward, attention turns toward the many ways sailors learned to read the land before it vanished completely. Chapter 2. Reading the Sea Near Land. The harbor has grown small behind the vessel, yet the coast still offers many quiet signs. The tower above the town remains visible against the evening sky. Farther along, a headland reaches into the water, its dark slope descending toward a narrow line of surf. Beyond it lies an island, low and rounded, with a small group of trees rising near its center. To an unfamiliar eye, these may be pleasant details in a fading landscape. To a sailor who knows the coast, they are useful marks. Before electronic position finding, navigation near shore depended on recognizing such features and understanding how their appearance changed as a vessel moved. Headlands, islands, mountain profiles, towers, buildings, solitary trees, beacons, and harbor entrances could all become part of a practical language. So could reefs, shoals, and changes in the shape of the shoreline, though some of these were revealed mainly by the behavior of the water around them. A navigator might look toward the tower and note its bearing. A bearing is the direction from the vessel toward an object. Another bearing might be taken toward the end of the headland. If both landmarks were known and shown on a chart, those two directions could help establish the vessel's position. The navigator could plot a line associated with each observed bearing. Where the lines crossed was an estimate of the ship's location. A third landmark might provide a useful check. The result depended on clear sight, correct identification, and careful measurement. Yet near a familiar coast, it could be remarkably helpful. The pilot aboard the vessel may not need to draw every line immediately. Long familiarity has taught the pilot how the marks should appear from different parts of the channel. The tower must remain just to the left of the wooded hill. The end of the headland should open slowly away from the island. If the spaces between them change too quickly, the current may be carrying the vessel sideways. This careful navigation through a harbor, river entrance, narrow channel, or other restricted water is called pilotage. It rests on detailed local knowledge, accumulated through repeated journeys and close observation. A pilot knows more than the shapes of the shore. The pilot may also know how the tide moves around a cape, where a river current presses across its mouth, and where an apparently calm patch of sea conceals shallow ground. The pilot remembers how these waters change with the tide, the wind, and the season, and how a vessel responds as it passes from one current into another. Ahead, two fixed marks come into view. One is a pale beacon near the water. The other is a taller post farther inland. From the correct part of the channel, they appear one directly behind the other, as though the distant post were standing upon the nearer beacon, or sometimes a range. When two fixed landmarks line up, they define a particular line across the water. By keeping the marks aligned, a vessel can remain on that line. In some places, a transit marks a safe way through a channel, with shallower water lying to either side. The helmsman makes a small adjustment. The nearer mark drifts toward the farther one until they are aligned again. The correction is slight, almost unnoticeable. Yet small corrections like this are the substance of careful coastal navigation. The channel passes beside a shoal. A shoal is shallow water or a shallow feature beneath the surface that may endanger a vessel. Some shoals are traced by breaking waves. In calm conditions, however, they can be difficult to see. Here the water over the sand appears paler than the deeper water nearby. The lookout watches the boundary between the two colors as it slides past the hull. Such changes can be useful, but their meaning is never universal. Water may change color because of depth, suspended sediment, underwater vegetation, reef material, plankton, or reflected light from clouds and sky. Pale water does not always mean sand, and dark water does not always mean safety. Each color must be interpreted within the setting of that particular place, weather, and hour. At a river mouth or harbor entrance, another shallow feature may appear. This is a harbor bar, a ridge of sand or sediment near the entrance. It may leave only limited depth for a vessel to cross, and the safest passage may change as water and sediment move. Local pilots knew when such entrances were most favorable. They understood how the tides and currents behaved around shoals, river mouths, capes, harbor bars, and narrow channels. They knew where the current might set the vessel to one side, where waves steepened over shallow ground, and where a channel offered deeper water. This was not mysterious intuition. It was expertise formed from memory, close observation, shared knowledge, and many passages made under different conditions. Other clues gathered around the vessel. A line of breaking water could suggest a reef or shallow bank. Seabirds might indicate nearby land, a feeding ground, or fishing boats. Drifting leaves and branches might have come from a river. A scent of damp earth, smoke, or vegetation could travel outward from the coast. Yet no bird, smell, patch of foam, or piece of drifting vegetation could provide a precise position by itself. Even surf required cautious interpretation. Waves may break over shallow ground, but their behavior is also shaped by wind, current, and other waves. Useful navigation came from comparing clues rather than trusting one sign alone. Sound, too, belonged to this coastal language. In darkness or fog, sailors might hear surf, bells, voices, or water moving among rocks. But sound does not always reveal distance reliably. A changing wind can carry it far from its source or turn it away. In fog, a sound may seem unusually near, faint, or displaced. A breaking shore heard clearly might still be farther away than expected. The pilot listens, but does not listen alone. Sound is considered beside the direction of the wind, the movement of the vessel, the known shape of the coast, and every other available sign. As evening deepens, a light appears on the shore. Coastal lights have a long history. Lighthouses existed in antiquity, often marking important approaches, but organized networks of dependable coastal lights expanded much later, especially during the 18th and 19th centuries. Even then, not every port possessed a lighthouse, and poor weather could hide a familiar light completely. In later lighthouse systems, lights could be made distinguishable from one another. One might differ from another in color, another might flash according to a repeated pattern or timing. The measured sequence of light and darkness could serve almost like a name. Sailors could consult written or charted descriptions of these characteristics to identify which light they were seeing. Such detailed descriptions belong mainly to more developed modern lighthouse systems, rather than to every period of seafaring. The light now visible astern shines for a moment, then is partly hidden as the vessel passes beyond the shoulder of the headland. The pilot notes the change. The harbor entrance can no longer be seen. The tower has merged with the hillside, and the two transit marks are lost among the shadows. For a while, the profile of the land remains recognizable. A low ridge slopes toward a rounded cape. A gap between hills marks the valley of a river. Then distance softens the shapes. Trees become indistinguishable from buildings. The coast is no longer a collection of separate marks, but a single dark line beneath the sky. Near land, the sea can be read through intimate details. A tower beside a hill, pale water above sand, the angle of a current, the measured alignment of two beacons. Each observation adds something, though none is complete by itself. Together they allow the navigator and pilot to build a careful understanding of the vessel's place within the coastal waters. But as the shore recedes, visible clues become less certain. Bearings are harder to take. Familiar shapes blend together. Sounds grow faint, and the patient knowledge of the pilot reaches the outer edge of its local world. The vessel continues into the evening. Behind it, the land settles lower on the horizon, until only the headland remains, a quiet darkness between water and sky. Inside the sheltered place where the course is kept, lamplight falls across an instrument mounted level and steady. Its circular card moves softly beneath a glass cover, trembling with the motion of the ship, before returning toward a familiar direction. With the coastline fading, the crew turns from visible landmarks to the compass, and to the invisible north it patiently seeks. Chapter 3. The Compass and the Invisible North. The compass card moves softly beneath its glass cover. As the vessel rises on a long swell, the card turns a little to one side. When the deck settles, it swings back again, guided by a force that cannot be seen, heard, or felt by the hand. A lamp burns nearby, its flame sheltered from the evening air. The helmsman watches the markings on the card and the fixed line above them. Beyond the ship, the last headland has nearly disappeared. There are no longer church towers, cliffs, or harbor beacons by which to judge the course. Yet within the compass case, a direction remains. At the heart of the instrument is a piece of magnetized material, traditionally a needle. When a magnetized needle is allowed to turn freely, it tends to settle along a roughly north and south line. This simple behavior had been observed long before the imagined voyage beneath our feet. Magnetized needles were known in China many centuries ago, and clear evidence of their use for maritime direction finding appears there by the 11th or 12th century. In Europe, clear written evidence of the maritime compass appears by the late 12th century. The knowledge did not belong to a single moment, nor did it travel along one simple path. Compass traditions developed, changed, and circulated through several regions. Travelers, scholars, craftspeople, merchants, and sailors carried useful ideas between communities. The history of that transmission is complex, as the history of many practical tools tends to be. Aboard ships, the important point was that the compass gradually became dependable enough to join the navigator's collection of trusted aids. Over time, the ship's compass took a familiar form. A magnetized needle was attached to a circular compass card marked with directions. As the vessel changed course beneath it, the card could rotate, continuing to align itself with Earth's magnetic field. A fixed mark inside the compass housing showed the direction in which the bow was pointing. This mark was called the lubber line. The name is old, but the idea is simple. The compass card turns, the lubber line remains fixed in alignment with the vessel. The direction on the card beneath that line is the ship's heading, meaning the direction its bow points at that moment. The helmsman watches this relationship carefully. If the intended heading drifts to one side of the lubber line, the rudder is adjusted. The ship responds slowly, for a vessel has weight and momentum. The card sways beneath the glass. Then after a few moments, the chosen direction returns beneath the fixed line. Early compass cards commonly divided the horizon into 32 points. Their names gave sailors a precise language of direction: north, northeast, east, and the finer points between them. Later navigators increasingly used degrees, dividing the full circle into 360 equal parts. The older compass points did not vanish at once. For a long time, both systems could be found in seafaring practice. The familiar star-shaped diagram that displays directions on a map is called a compass rose. On the instrument, the divisions help the helmsman hold a heading. On a chart, a compass rose helps the navigator draw and read directions across the page. In this way, the ordered horizon can be carried from the moving deck to the quiet surface of paper. Yet the compass, useful as it is, does not reveal the ship's position. A heading answers one question: which way is the bow pointing? Position answers another: where is the ship? A vessel may steer west for an hour, but its position afterward will also depend on its speed, the current, the wind, and the accuracy with which the course was held. The ship may be pressed a little sideways even while its bow remains on the chosen heading. The compass therefore supplies one important part of navigation, but never the whole of it. Nor does the compass needle point precisely toward the geographic North Pole. The direction toward the geographic North Pole is called true north. It belongs to the geometry of the rotating Earth and to the imaginary lines of longitude that meet at the pole. Magnetic north, by contrast, is the direction indicated by the local horizontal component of Earth's magnetic field. Put more simply, it is the direction in which that field draws a freely turning compass along the horizon. True north and magnetic north are usually not identical. The angle between them is known as magnetic variation, also called magnetic declination. In one region, the compass may point somewhat east of true north. In another, it may point west. The amount differs from place to place, and it changes gradually over time as Earth's magnetic field changes. For the navigator, this meant that a compass reading often needed correction. If the local variation was known, a magnetic heading could be converted into a direction measured from true north. Knowledge of the variation might come from previous observations, from tables, from notes written on a chart, or from comparison with a direction found through the sun or stars. The distinction was important but manageable. The navigator did not expect the instrument to possess perfect certainty. Instead, its behavior was observed, recorded, compared, and corrected. There was also another source of error, and this one came from much closer at hand. Iron aboard the vessel could influence the compass. Magnetized tools, guns, metal cargo, and other fittings might draw the needle slightly away from the direction it would otherwise take. On later vessels, iron or steel hulls produced much larger magnetic influences, requiring careful checking and compensation. This ship-specific compass error is called deviation. Variation and deviation may sound similar, but they arise from different causes. Variation comes mainly from Earth's magnetic field. It describes the difference between magnetic north and true north at a particular place and time. Deviation comes from magnetic influences aboard the vessel itself. Deviation can even change when the ship turns. On a new heading, the compass occupies a different angle in relation to the surrounding iron, cargo, tools, guns, or hull. A reading that is affected in one way while the ship points east may be affected differently when the bow points south or west. Once again, the navigator's task is not to assume perfection, but to notice a pattern. Navigators learn to test these errors rather than merely hope they were small. They could compare a compass bearing with a direction determined astronomically. The rising or setting sun, or a suitable star observed at a known time, could provide a reference. The difference between the expected direction and the compass reading helped reveal the total compass error. The navigator could better understand how the instrument behaved on different headings. Such knowledge could be preserved in written notes and consulted when the vessel turned onto a new course. A compass, then, was not a mysterious arrow that always pointed toward one perfect place. It was a sensitive instrument made useful through experience. Its value came from its steady, repeatable guidance. Even under cloud, and even beyond sight of land, it offered a direction that could be watched hour after hour. At the helm, the chosen point remains close to the lubber line. The vessel does not hold it without effort. A wave turns the bow slightly, a gust presses against the sails, the rudder answers, and the heading slowly returns. Around the compass, the timber creaks with the long movement of the sea. The helmsman does not stare rigidly at the card. There is a rhythm to the work. A glance at the compass, a look toward the sails, and another glance into the darkness ahead. The ship moves between small corrections. It wanders a little and is gently brought back. From time to time, the navigator also looks down at the card. The reading may require correction for variation. It may need allowance for deviation. Wind and current may still carry the vessel sideways, even when the heading is held with care. None of these uncertainties makes the compass useless. They simply remind the crew that navigation is an art of comparison, patience, and adjustment. The compass gives them a steady beginning, a repeatable direction in a wide and otherwise unmarked space. The coast is gone now. Sea and sky meet in a dim circle around the vessel. Inside the compass housing, however, the horizon has been made small enough to fit beneath glass. It is divided into points and degrees, while north is quietly indicated by the turning card. The lamp flame trembles, the ship rolls, and the markings drift briefly away from the lubber line. Then the card settles once more. A heading held through the night becomes more useful when it can be recorded. Near the compass, the navigator's chart waits beneath the lamplight. Across its pale surface run compass roses and fine lines, while coastal names follow the careful shapes of distant shores. Soon the direction beneath the lubber line will become a line drawn on paper. Chapter 4. Charts, portolan maps, and lines across water. The chart rests upon a broad wooden table, held flat by small weights at its corners. In the warm light of an oil lamp, the sheet seems almost the color of sand. Its surface is covered with fine marks. Coastlines bend around bays. Names gather beside harbors. Numbers, circles, small symbols, and slender lines extend across the water. The navigator places one finger near the harbor left behind. Slowly, that finger moves toward the ship's intended destination, although the destination itself remains far beyond the dark horizon. Between the two places lies open sea, reduced for a moment to the quiet space of paper. A nautical chart is not merely a picture of the world, and it is not intended mainly for decoration. It is a working navigational document. Its purpose is to emphasize the details a sailor may need, including coasts, hazards, depths, directions, and aids to navigation. A chart gives particular attention to the meeting place of land and water. A general map may show roads, kingdoms, rivers, and mountain ranges far inland. A sea chart may leave much of the interior nearly empty, while carefully recording every known inlet, island, headland, reef, and sheltered anchorage along the shore. This practical emphasis gives the chart its quiet, purposeful character. Every curve and symbol may answer a question that a sailor will eventually ask. Where does the coast turn? How deep is the channel? Is there a shoal near the harbor entrance? What landmark, light, or buoy may guide the vessel toward safety? Among the best-known early sea charts were the Portolan charts, which appeared in the Mediterranean by the late 13th century. They were shaped by the needs of mariners moving between ports, and they gave careful attention to coastlines and coastal names. On many Portolan charts, place names gathered so closely along the shore that the writing seemed to form another coastline made of ink. Important ports might stand out more strongly. Meanwhile, inland geography often received limited attention. The chart maker's chief concern was the coast, where the shape of a cape, the position of an island, or the opening of a harbor could matter greatly to a vessel at sea. Across the water ran dense networks of radiating direction lines. They spread from several points, crossed one another, and formed orderly patterns over the seas. Compass roses or wind roses also appeared, helping the navigator think about the directions between one harbor and another. These networks were not records of ships' actual tracks. They should not be imagined as trails left by earlier vessels, nor should their construction be oversimplified by treating them as identical to the mathematically defined rhumb lines used on later charts. The precise way these Portolan networks were formed, and their relationship to later navigational systems, is more complicated. Their practical value, however, is easy to appreciate. The lines helped mariners visualize sailing directions across an otherwise unmarked stretch of water. A sailor could look from a known port toward another coastal point and consider the direction that connected them. Under the lamp, the navigator follows one of these imagined paths with a fingertip. The movement is small and gentle. On the actual sea, the same passage may require days of steady sailing. A line placed on a chart can represent a course, meaning an intended direction of travel. The ship's heading is slightly different. Heading is the direction in which the bow is pointing at a particular moment. Course and heading may be close, but they are not always the same. Wind may press against the sails and hull. A current may carry the vessel sideways. The bow may remain pointed toward one part of the horizon, while the ship's true movement shifts gradually toward another. For this reason, a line on the chart is not necessarily a perfect trace of the vessel's path. At first, it is an intention. Later, it may become an estimate of what the ship has done. As methods of chart-making developed, navigators increasingly worked with routes known as rhumb lines. A rhumb line crosses all meridians at the same angle. Meridians are the imaginary north to south lines used in measuring longitude. A vessel following a rhumb line maintains a constant compass bearing, with the necessary compass corrections taken into account. There is a difficulty in placing such a route on paper. Earth is curved, while the chart is flat. Any method of representing the curved surface of Earth on a flat sheet must alter something. This method of representation is called a projection. In 1569, Gerardus Mercator introduced the projection that now bears his name. The Mercator projection is cylindrical. It may be imagined as a way of transferring the globe onto a cylinder and then opening that cylinder into a flat sheet. On this projection, rhumb lines appear straight, making it convenient to draw and follow a constant compass bearing. Yet that convenience comes with distortion. Areas far from the equator appear larger than they truly are. This is a reminder that no flat chart can reproduce every quality of a curved world perfectly. A projection may make one kind of navigational task easier, while changing the appearance of distance, shape, or area elsewhere. The earlier Portolan charts predated the Mercator projection. They should not simply be called Mercator charts, because they came from different traditions and were constructed in different ways. Portolan charts could be very useful in the regions for which they were made, especially where generations of sailors had repeatedly traveled the same waters. Still, useful did not mean flawless. Every chart was made from human observation. Information gathered during many voyages could be assembled, compared, copied, and revised. A newly observed headland might be added. A coastline might be adjusted after another passage. Reports from mariners and pilots could help fill spaces that had once been uncertain. In this way, a chart was never entirely the work of a single moment. It gathered knowledge slowly. One voyage contributed a bearing, another contributed an estimated distance, another brought news of a reef, an unfamiliar current, or a harbor entrance that had been drawn incorrectly. Over time, the sheet became a record of many watchful journeys. Uncertainty entered by the same path. Copying errors could move from one chart to the next. A line might shift slightly under a copyist's hand. A misunderstood report could place an island too far east or west. Some information was kept secret, and some coasts had not been surveyed carefully. Incomplete observations left gaps that could not be repaired by confidence alone. Longitude created particular difficulty. Before sailors could determine east to west position reliably, the open ocean coordinates of islands and coasts might be uncertain. A coastline could look convincing in shape while being misplaced on the wider world. Accurate coastal outlines did not guarantee accurate open ocean coordinates. Even as charts began to include latitude and longitude scales more regularly, the charted position of a reef, cape, shoal, or island was not necessarily exact. Ink could appear calm and authoritative, but the mark still depended on the quality of the observations behind it. Experienced mariners therefore did not surrender their judgment to the chart. They compared it with what they saw, heard, measured, and remembered. Written sailing directions remained important because no chart could contain every local warning. Such directions could describe how one headland aligned with another, where a tide ran strongly, or what signs indicated the approach to a difficult harbor. They could preserve details that were awkward to fit among the lines and symbols of a crowded sheet. Local pilots carried further knowledge in memory. A person who had spent years sailing one coast might know how the water changed with the tide, where a current turned, or how a familiar headland appeared in haze. Maps were not automatically superior to oral knowledge. The two often complemented each other. The chart provided a broad arrangement of places. Written directions added explanation. The pilot supplied the fine texture of experience. As surveying and chart-making developed, charts gradually became more crowded with practical information. Latitude and longitude scales helped define position. Numbers showed soundings, meaning measured depths of water. Short descriptions indicated whether the seabed was mud, sand, shells, or gravel. Reefs and shoals were marked. Notes described tides and currents. Lighthouse information helped navigators recognize lights after sunset. Buoy information guided vessels through channels and around hazards. Each added detail made the chart more useful, though never perfectly complete. Every mark began with an observation. Someone had lowered a line and measured a depth. Someone had brought up a sample of sand or mud from the seabed. Someone had watched a current, recorded a tide, observed a light, or noted the place where shallow water began. The chart gathered these separate moments and preserved them for another crew on another night. The navigator studies the pale sheet beneath the lamp. A finger moves slowly from harbor to harbor, pausing at a headland and then crossing the open water toward a distant coast. Outside, the vessel rises and settles with the waves. The sea itself contains no printed names, no compass roses, and no fine networks of ink. The chart gives those invisible relationships a form. It allows direction to be considered before the distant coast can be seen. It warns of known dangers and preserves the remembered shape of land beyond the horizon. Yet it cannot promise that every feature lies exactly where the paper claims, so the navigator compares. The compass provides a heading, the chart suggests a course, written directions offer local warnings, memory adds details that symbols cannot hold. Each source supports the others, and uncertainty is met with patient attention rather than with trust in any single clue. A fine course line is drawn outward from the last estimated position. The pencil moves quietly across the sheet. Beyond the cabin, water folds along the hull, and the compass card continues its gentle motion beneath glass. The line points toward the place where the vessel is meant to go, but direction alone cannot reveal where the ship is now. The line still lacks movement. It cannot say how much water has passed beneath the keel or how far the vessel has traveled since the coast disappeared. But the sea does not measure itself. As the ship proceeds into darkness, another quiet question waits beside the lamp. How far has the vessel truly traveled? Chapter 5. Measuring Speed and Keeping a Reckoning. The course line beneath the navigator's pencil points steadily across the chart, but it cannot say how quickly the ship moves along it. Direction is only one part of the answer. To estimate a position in open water, sailors must also judge distance, and distance at sea is found by bringing together speed and time. Outside the chart room, the vessel advances beneath the moon. A pale wake opens behind the stern, lingers for a moment, and settles back into the wider sea. There are no milestones here, and no roadside trees passing at regular intervals. The water itself is moving, and the ship travels within that movement. At first, sailors estimated speed through careful observation. They watched the passing water, the foam beside the hull, and the changing shape of the wake. With experience, they learned to recognize subtle changes in the vessel's pace, the pressure of wind against the sails, the sounds within the rigging, and the rhythm of the hull meeting the waves, all offered quiet clues. Such judgments could become remarkably practiced, but they were difficult to preserve in a calculation. Navigators needed a method that could turn movement into a number, and then allow that number to be recorded and compared with later observations. Over time, sailors in some maritime traditions developed several forms of an instrument called the log. One common device in early modern European sailing was the chip log. It was simple in appearance. A weighted wooden sector was attached to a long line. When the sector was cast astern, it remained relatively steady in the water while the vessel continued forward. As the ship moved away from the wooden piece, the line paid out behind the stern. Knots or other marks were placed along the line at measured intervals. At nearly the same moment that the sector entered the sea, a small sandglass was turned. Sand passed through its narrow opening for a short period. When the measured time had elapsed, the line was stopped, and the sailors counted how many marked intervals had run out. That count gave an estimate of the ship's speed through the water. The exact details were not the same in every place or period. The spacing of the marks varied. Sandglasses could measure different intervals, and definitions of the nautical mile were not always identical. Nor was the chip log used in every culture or every century. It was one solution among many, developed within particular traditions of seafaring. Its principle, however, was clear. A measured length of line was allowed to run out during a measured length of time. Together, the line and the glass gave the crew a practical estimate of speed. From marked log lines came the use of the word knot as a unit of speed. 1 knot means 1 nautical mile per hour. Today, a nautical mile is internationally defined as 1,852 meters. Earlier, sailors worked with the measures and standards known in their own time, so their arrangements should not be imagined as perfectly uniform from one voyage or century to another. On the moonlit stern, the sandglass empties, the line is stopped, the count is called softly, and the wooden sector is drawn back aboard. Water beads along the cord. For an instant, each drop catches a small reflection of the lamp. A single measurement cannot describe an entire voyage. Wind changes, sails are adjusted, waves rise and ease. The vessel may move briskly for a time, then slow beneath lighter air. Because the ship's speed changes, the measurement must be repeated through the watches, the regular periods into which work aboard ship is divided. Again the line is cast, again the glass is turned. Course, estimated speed, and elapsed time are recorded, watch after watch. Some crews used a traverse board to preserve these short-term observations. A traverse board was a pegboard on which pegs could mark the direction steered and the estimated speeds during successive portions of a watch. It served as a practical memory until the information could be transferred into written calculations. During one watch, the helmsman might steer in one direction for a while, and then alter course. The log might show one speed early in the watch, and another later. Each observation represented only a portion of the ship's movement. Near the watch's end, those portions could be brought together and entered into the written record. The navigator then used them to continue the ship's reckoning. This method was called dead reckoning. The exact origin of the expression is uncertain. It may be related to the words deduced reckoning, though this explanation remains debated. Whatever the source of the name, the method itself was straightforward in principle. The navigator began with a known or assumed earlier position. From that starting point, the navigator applied the direction traveled, the estimated speed, and the elapsed time. The result was an estimate of the vessel's present position. Dead reckoning was not a random guess. It was a disciplined calculation based on imperfect observations. If a ship maintained a course for a certain length of time, at an estimated speed, the navigator could judge how far it ought to have traveled. That progress could then be marked upon the chart. If the course changed or the speed rose or fell, the reckoning changed as well. The new point showed the place where the vessel was expected to be. Expected was an important word. A compass heading tells the direction in which the bow is pointed, but it does not always reveal the ship's exact path across the earth. Wind blowing from the side may push the entire vessel sideways, even while the bow remains turned toward the chosen heading. This sideways movement is called leeway. Sailors tried to estimate leeway from the strength and direction of the wind, and from the way the vessel moved through the water, yet the amount could not always be known precisely. A ship might hold a steady heading and still drift gently away from the line drawn on the chart. Currents created another quiet displacement. A current is moving water, and a vessel carried within it may pass over the seabed in a different direction or at a different speed from the one suggested by its motion through the surrounding water. The distinction is subtle but important. A log estimates speed through the water. It does not necessarily reveal speed over the seabed. A following current may carry the ship onward, increasing its progress over the ground. An opposing current may reduce that progress. A cross current may move the vessel gradually to one side. The ship can travel steadily through the water, while the water itself carries the ship elsewhere. Navigators allowed for known currents and likely leeway whenever they could. Sailing directions, previous experience, and observations of the sea might help. Still, these influences were not always visible, and they were rarely known with complete accuracy. A small error in speed could seem unimportant during one short watch. A slight error in direction might appear no wider than a pencil line. Over many hours, however, these differences accumulated. After days without a reliable sight of land or sky, the true position could be substantially removed from the reckoned one. For this reason, a dead reckoned position remained provisional. It was the best conclusion available from the evidence collected so far, not a promise of perfect certainty. Beside the lamp, the navigator reviews the watch. The courses steered are gathered from the short-term record. Speeds are taken from repeated estimates. Elapsed time is measured through the steady rhythm of watches and sand glasses. An allowance may be made for wind pressing against the vessel's side, and another for a current thought to be moving beneath it. Then the pencil advances across the chart. Around it lies an invisible region of uncertainty. It may be narrow after a recent dependable observation. It may grow broader after long hours of cloud, changing wind, or an unfamiliar current. Skillful navigation includes an awareness of this uncertainty. The careful navigator asks not only, where ought we to be, but also, how far from that point might we truly be? The vessel continues through the night. Behind it, the wake slips into moonlight and fades. Another sand glass is turned. Another entry waits to be made. Line, glass, pegboard, written record, and chart. Through this patient rhythm, the crew turns motion into a record, and the record into an estimated place upon the sea. Each estimate begins with what was known before, and carries that knowledge forward, watch by watch, into the darkness ahead. The reckoning suggests where the ship ought to be. Yet when uncertainty gathers, especially in fog or near a shallow coast, the navigator may seek another kind of evidence. The surface can carry the vessel unseen, but beneath it lies a hidden landscape of banks, channels, mud, sand, shells, gravel, and stone. When the charted point is no longer quite enough, the crew can lower a line and ask the sea beneath them for another answer. Chapter 6. Soundings and the Hidden Seabed. The ship moves more slowly now. A pale fog has settled over the water, softening the boundary between sea and air. Beyond the rail, there is no clear horizon, only a quiet gray distance in which every shape seems to have withdrawn. The sails remain gently filled, and the timbers answer the waves with an occasional low creak. The reckoning on the chart suggests that land may lie somewhere ahead, but the coast cannot yet be seen. No headland rises through the mist. No tower or harbor light offers a bearing. In such conditions, sailors turn their attention away from the hidden shore and toward the hidden ground beneath the vessel. Near the bow, a sailor prepares a lead line. It is a simple instrument, a weight made of lead, attached to a long, carefully marked rope or line. The marks are arranged so that the sailor can recognize how much line has passed overboard, sometimes by sight and sometimes by touch alone. The ship's motion is steadied as much as possible. Loose coils are gathered so that they will run freely. Then the lead is swung outward and released. There is a small splash. The weight disappears into the gray water. The line follows, slipping steadily through practiced hands. For a moment, the lead descends through a world no one aboard can see. At last, it reaches the seabed, and the line relaxes. This measurement is called a sounding. The word may mean the act of measuring the water's depth, or the depth obtained from that measurement. When the lead touches bottom, the length of line paid out indicates how much water lies beneath the ship. Depth was traditionally expressed in fathoms. A fathom is now equal to 6 feet, or about 1.83 meters. A report of 10 fathoms meant that the seabed lay about 60 feet below the surface. The line carried a sequence of recognizable marks. Different materials might be fastened at particular depths. One place might be marked with leather, another with cloth, and another with a texture familiar to the sailor's hand. At night or in dense fog, the wet line could be read by touch, when it could not easily be read by sight. Not every portion of the line had a special mark. This distinction produced traditional depth calls. If the water reached a marked place, the call might begin with the words, "By the mark." If the depth fell between marks and had to be estimated, the call might begin, "By the deep." These brief phrases formed part of a practical language that could carry clearly across the deck. The line is drawn in again. Wet rope settles into coils. The sailor calls the measured depth, and another crew member records it. On its own, the number is useful but incomplete. The same depth can be found in many bays, channels, and coastal approaches, yet repeated soundings can begin to reveal a pattern. A little later, the lead goes over once more, splash, pause, and the depth is called. If each measurement is shallower than the one before it, the water is said to be shoaling. Shoaling means becoming progressively shallower. It may suggest that the vessel is approaching a bank, a broad shelf, or the gradual rise of the seabed near a coast. The change can be more informative than a single measurement. 30 fathoms, then 25, then 20. The sequence tells a quiet story of the hidden ground rising below. Soundings were especially useful in regions with broad, shallow continental shelves. There, the seabed could rise gradually over a great distance. Regular measurements might offer early notice that a ship was nearing land, even while the coast remained beyond sight. Depth was not the only message brought up by the lead. Many sounding leads had a hollow in the base. Before casting, sailors could fill this hollow with tallow. Tallow is rendered animal fat, and it was once used as a sticky material in the bottom of the lead. When the weight struck the seabed, grains and fragments pressed into the tallow. The lead could then return carrying a small sample from the unseen landscape below. The sailor draws the weight aboard and turns its base toward the lantern. Embedded in the pale tallow are grains of sand, tiny shell fragments, and a trace of dark mud. Another cast, in another place, might bring up gravel or small stones. These modest particles offered an additional clue. Charts and sailing directions sometimes described not only the depth of an approach, but also the character of its bottom. A chart might mention fine sand in one area, mud in another, shells near a bank, or gravel beside a channel. Local pilots remembered similar patterns as part of their coastal knowledge. The seabed possessed a geography of its own, although none of it could be seen from the deck. The sample is compared with the chart notes. Its mud and shell fragments seem consistent with the waters the navigator expects to find here. Yet no one treats this as final proof. Mud occurs along many coasts. Sand covers wide stretches of seabed. Shells, gravel, and small stones are not unique to one place. Soundings could help identify a coast only when combined with other evidence and sound local knowledge. The navigator considers the measured depths, the pattern of shoaling, the estimated course, the compass heading, the wind, the current, and the observations preserved by sailors who have passed through these waters before. Even the measured depth contains some uncertainty. If the ship is moving, or if a current pulls across the line, the rope may tilt rather than hang straight downward. A slanting line is longer than the direct vertical distance from the surface to the bottom. The reading may therefore make the water appear deeper than it truly is. Experienced sailors tried to cast the lead ahead of the vessel, timing the work so that the line stood nearly upright when the weight touched bottom. This required strength, coordination, and close attention to the ship's movement. A hand lead was useful in relatively shallow water, particularly near coasts, banks, and channels. Farther offshore, where the water was deeper, heavier deep-sea leads and much longer lines were required. Lowering them took time. Drawing them back aboard demanded patient labor. Deep water sounding from a moving sailing vessel was especially difficult. Waves, currents, and the vessel's own progress could pull the long line away from the vertical. The process was slow and sometimes uncertain. Soundings were therefore most immediately helpful where the seabed had already risen within reach of the line. In darkness or fog, when familiar landmarks had disappeared, the lead offered something direct and physical. It allowed the crew to touch the hidden world beneath them, one measured point at a time. Again, the line is prepared. Again, the lead arcs outward and falls. The fog absorbs the sound of its entry. The crew waits while the rope runs through the sailor's hands. Then comes the subtle change that means the weight has found the bottom. The depth is called. The number is entered into the record. The lead is hauled aboard, and its small sample is examined beneath the lantern. The water is shallower than before, though only a little. The material in the tallow agrees with the chart's description, but the navigator keeps the ship under a cautious spread of sail. There is no need to claim certainty too soon. Each sounding narrows the possibilities, just as each compass observation and each entry in the logbook has done. Below the hull, an unseen landscape rises gradually through the darkness. There are slopes of sand, level beds of mud, scattered shells, gravel, banks shaped by currents, and channels followed by the tide. The lead touches this landscape only briefly, at one small point, before returning to the deck with its measured clue. Above, the fog begins to loosen. The gray ceiling thins and a deeper blue appears beyond it. The crew has listened downward to the seabed, but navigation has always required attention in more than one direction. As the clouds quietly part, the first stars become visible above the mast. They are faint at first, then steady, offering another ancient pattern of guidance across the open water. Chapter 7. The Night Sky as a Guide. At first, only one star shows through the thinning cloud, pale and quiet above the mast. Then another appears farther west, and another near the edge of the clearing sky. The fog loosens into long gray veils. Between them, the blue of evening deepens, and the stars emerge one by one, as though the darkness were slowly revealing lights that had been there all along. The sailor at the helm glances upward. The navigator does the same. A short while ago, their attention was directed beneath the ship, toward the lead line and the hidden seabed. Now it turns toward the open sky. Long before electronic receivers could calculate a vessel's position, the heavens offered sailors a broad and familiar field of guidance. The stars could indicate direction. Their changing appearance could mark the season and suggest when a known period of travel was approaching. With careful observation, they could also help a navigator estimate where the ship lay upon the curved surface of Earth. Yet the sky did not provide one simple answer. A single star rarely supplied a complete position. Celestial navigation depended on memory, comparison, timing, a visible horizon, and knowledge passed carefully from one observer to another. As the ship moves onward, the stars seem to travel slowly across the heavens from east to west. They rise, climb, and later descend toward the opposite horizon. This movement is apparent rather than literal. Earth is turning from west to east, while the distant stars appear to sweep in the other direction. To describe the sky, astronomers sometimes imagine a vast globe surrounding Earth. This is called the celestial sphere. The stars, moon, sun, and planets appear to lie upon its inner surface, although in reality they are at many different distances. The celestial sphere is not a physical shell. It is a useful picture, a way to describe where lights appear in the sky and how they seem to move. Earth's axis, the imaginary line around which the planet rotates, can also be imagined as extending outward into the celestial sphere. The two imaginary points where this axis meets the sky are called the celestial poles. As Earth turns, the stars appear to circle around them. Near a celestial pole, a star traces a small, slow circle. Farther away, stars follow wider paths. Some rise above the horizon and later set. Others, depending on the observer's location, may remain visible throughout the night, circling without dipping below the dark edge of the sea. The sky seen by any navigator depends partly upon latitude, the north-south position on Earth. A change in latitude alters which stars are visible and how high their paths seem to rise. The season matters too, because different parts of the nighttime sky come into view at different times of year. The hour of night changes the scene further, as one group of stars descends and another rises. Weather also shapes what can be seen. Cloud may conceal half the heavens. Haze can soften the lower stars until they disappear. Fog may erase the horizon completely, while rough seas make every observation rise and fall with the deck. Bright twilight can overwhelm all but the clearest lights. On this evening, however, the horizon is becoming distinct. A narrow line separates sea from sky, and that line is valuable. Celestial observations work best when a navigator can compare the position of a star with a clear, well-defined horizon. Without that reference, judging height or direction becomes more difficult. Still, precision was not always expressed through numbers. Across centuries and oceans, navigators organized their knowledge of the sky in many different ways. In the Mediterranean, across the Indian Ocean, on seas traveled by Arab, Chinese, and European mariners, and throughout the broad Pacific known to generations of indigenous wayfinders, people observed the heavens from different shores. They grouped stars differently, gave them different names, and connected them with different stories, seasons, directions, and routes. A familiar grouping of stars is often called a constellation. In ordinary and historical use, this may mean a pattern recognized within a particular culture. Perhaps a figure, a creature, a tool, a pathway, or another meaningful shape. In modern astronomy, a constellation can also mean an officially defined region of the sky, enclosed by agreed boundaries. The patterns themselves are culturally created. The stars do not arrive already joined by invisible lines. One society may recognize a single figure, or another recognizes several. Some navigators may pay special attention not to a large picture, but to a pair of bright stars, a dark space in the Milky Way, or a sequence of lights appearing through the night. It would therefore be misleading to assume that all navigators used the formal constellation names familiar from European charts. The heavens held many systems of order, each shaped by language, place, practice, and patient observation. Some navigational traditions emphasized numerical angles and written astronomical tables. Observers could compare the predicted positions of stars, the moon, or planets with what they saw above the horizon. Other traditions emphasized memorized star paths, rising and setting points, swells, winds, and sequences of directions along a known route. These were not steps on a ladder leading from folklore towards science. They were different ways of organizing sophisticated observational knowledge. Each depended upon close attention, teaching, correction, memory, and experience. Each could preserve what many generations had learned from repeated journeys. A navigator might steer toward the place where a particular star rose. As that star climbed and became less convenient as a marker, another could take its place. Later, a third might appear in a useful part of the sky. In this way, a route could be remembered as a sequence of stars, with each one guiding a portion of the night. A star's precise rising or setting point changes somewhat with latitude and with atmospheric conditions near the horizon. Even so, familiar stars could provide useful directional references when interpreted with care. They did not need to offer perfect certainty. They needed to be recognized, understood, and compared with other signs. The stars also helped mark the turning of the seasons. Their first appearance before dawn, or their return to the evening sky after a period of absence, could identify a familiar part of the year. In this way, knowledge of the sky helped navigators remember seasons and suitable periods of travel. The heavens served not only as a compass, but also as a broad and slowly changing calendar. Not every bright light behaves in quite the same way. Most stars keep nearly fixed patterns relative to one another during a human lifetime. Planets, by contrast, move against the background of the stars. Because their positions change, a navigator could not always treat them like fixed points in a familiar pattern. Using a planet required suitable knowledge or astronomical tables predicting where it would appear. The moon also changes position noticeably from night to night, and even during a single night. Yet when their positions were understood or predicted, the moon and bright planets could support navigation as well. For now, the navigator aboard the ship simply watches the clearing sky. No instrument is lifted. There is value in looking before measuring. Above the mainmast, one pattern has tilted westward since it first appeared. Another cluster is rising from the dark eastern sea. The sailor at the helm holds a steady compass heading, while the changing sky provides a second, independent sense of direction. Neither clue is accepted alone. The compass may be affected by magnetic variation or by iron aboard the vessel. A star may be hidden by cloud, softened by haze, or viewed from an unfamiliar latitude. Agreement among several signs is more reassuring than confidence placed in only one. The navigator watches how one bright point rises from the eastern horizon. Its position is familiar, though not exact. Then attention shifts to the compass card beneath its glass. and afterward to the quiet movement of the sea. Each observation belongs beside the others. Together they offer guidance that no single sign could provide. The ship continues beneath the widening night. Water lifts against the hull and settles again. Timber answers with a low creak. Behind the vessel, the last traces of fog drift over the wake, while ahead the horizon remains open and dark. To an unpracticed eye, the stars may seem scattered almost without order. To someone trained in their movements, they form a field of remembered relationships. One light follows another. One path leans toward the south. One rising point belongs to a known direction. One seasonal appearance recalls a familiar time of travel. These relationships could be held in written tables, traced on charts, expressed through measured angles, or remembered in practice sequences. They could be taught through names and patterns, or joined with knowledge of winds, swells, and routes. The form varied from one navigational tradition to another, but the patient attention beneath it was shared. The night sky was never entirely still, and it was never completely dependable. Clouds could close over it. Twilight could hide it. The horizon could vanish into mist. Yet when conditions allowed, the heavens offered a wide frame of reference above waters where no road or landmark could be seen. Now the last strips of cloud draw away, stars extend from one horizon to the other, their apparent paths shaped by Earth's quiet rotation. The ship moves beneath them, carrying its compass, charts, records, and accumulated knowledge through the dark. And among the slowly turning lights of the northern sky, one star seems almost still. It is not perfectly fixed, yet for many sailors it became a patient companion in the work of finding latitude. Chapter 8. Polaris and Finding Latitude. Above the dark northern sea, the stars appear to turn in a wide, patient circle. Some rise from the eastern horizon, others descend toward the west. Between them, near the center of this slow celestial wheel, Polaris seems almost to remain in place. The navigator watches from the open deck. Polaris is not the brightest star in the sky, nor is it perfectly still. Yet its position offers something remarkably useful, a way to estimate how far north the vessel has traveled. That north and south position is called latitude. Latitude measures angular distance north or south of the equator. The equator itself is 0 degrees of latitude. The North Pole is 90 degrees north, and the South Pole is 90 degrees south. Between them lie the harbors, capes, islands, and open waters of the world, each resting upon an imagined circle running east and west. To understand how a star can reveal latitude, it helps first to look toward the horizon. The visible horizon, the distant boundary where sea and sky appear to meet, is treated as 0 degrees. From there, an observer may imagine an arc rising through the sky. Directly overhead is a point called the zenith, with an altitude of 90 degrees. Altitude in navigation means the angle of an object above the horizon. A star resting at the horizon has an altitude near 0 degrees. A star halfway from the horizon to the zenith has an altitude of about 45 degrees. If the star were directly overhead, its altitude would be 90 degrees. The navigator is not trying to measure how many miles away a star might be. Such a distance lies far beyond the practical needs of the voyage. Instead, the navigator measures the angle between the horizon and the star. In the northern hemisphere, the altitude of the north celestial pole is approximately equal to the observer's latitude. The north celestial pole is the point in the sky toward which Earth's northern rotational axis points. As Earth turns, the stars seem to travel in circles around it. Polaris lies very near this point. If Polaris appears about 20 degrees above the northern horizon, the observer is near 20 degrees north latitude. If it appears 40 degrees high, the observer is near 40 degrees north. As a vessel travels farther north, Polaris climbs higher in the sky. At the North Pole, it would appear almost directly overhead. This relationship gave navigators a clear and memorable guide. It is often expressed in a simple phrase: the altitude of Polaris equals latitude. For careful work, however, this is only an approximation. Polaris does not sit exactly at the north celestial pole. At present, it lies less than 1 degree away. As the sky appears to turn, the star traces a small circle around the true pole. During many early modern voyages, Polaris was farther from the pole than it is now. Navigators seeking greater accuracy could apply corrections from tables or observe Polaris in relation to surrounding stars. Its usefulness has also changed across the longer passage of centuries because of precession. Precession is the slow change in the direction of Earth's rotational axis, rather like the gradual wandering of the axis of a gently turning top. The complete movement takes many thousands of years. Because of it, the celestial poles do not always point toward the same stars. Polaris is a particularly helpful pole star in the present age, but it has not always occupied so favorable a position. Tonight it remains a quiet reference above the vessel's northern rail. The navigator raises an instrument and waits for the rolling deck to settle into a rhythm. Measuring an angle from a moving ship is never as simple as drawing one upon paper. The horizon lifts and falls. The observer's body moves with the hull. Haze may soften the boundary between water and sky. Even so, observations can be repeated, compared, corrected, and entered into a notebook. Over the centuries, sailors and astronomers used many instruments for this work. These included astrolabes, quadrants, cross-staffs, backstaffs, and later, octants and sextants. Their designs differed, but each helped an observer measure the angular altitude of a star or the sun. A cross-staff was direct in appearance. It consisted of a long staff and a shorter crosspiece that could slide along it. The observer looked along the main staff and moved the crosspiece until one end appeared to touch the horizon, while the other aligned with the celestial body. The position of the crosspiece then indicated the angle. For stars, the method could be useful in clear weather. For the sun, it brought an obvious difficulty. Looking toward the sun was uncomfortable and hazardous, and its bright glare could make a delicate observation harder. The backstaff, associated especially with John Davis in the late 16th century, offered another approach. It allowed the observer to face away from the sun. The sun's shadow and the visible horizon could then be used together, sparing the navigator from looking directly into the intense light. The vessel's astronomical work did not depend upon Polaris alone. Latitude could also be found from the sun's altitude near local noon, when the sun reached its highest point for that day. This required knowing the sun's declination, meaning its angular position north or south of the celestial equator. The celestial equator may be imagined as Earth's equator projected outward upon the sky. Because Earth travels around the sun with its axis tilted, the sun's declination changes with the seasons. Navigators used astronomical tables to find the expected declination for a particular date. By combining that information with the sun's altitude near noon, they could estimate latitude without relying upon a visible northern star. Such methods were especially important in the southern hemisphere, where Polaris cannot be seen. There is no comparably bright star near the south celestial pole. Southern navigators could use other stars and constellations, including the Southern Cross, with appropriate methods, but the Southern Cross does not itself sit at the south celestial pole. When interpreted correctly, it can help indicate the pole's general region, but it is not a bright southern equivalent of Polaris. Even in northern waters, Polaris was not always convenient. At low northern latitudes, close to the equator, it appeared very low above the horizon. There, mist, clouds, waves, or the shifting edge of a heaving sea could conceal it. South of the equator, it disappeared entirely. A capable navigator therefore learned more than one way to find latitude. And not every sailor aboard personally made astronomical observations or performed the calculations. This work required training, suitable instruments, and tables, and regular practice. On many vessels, the master, pilot, or another experienced officer took the sights and maintained the written reckoning. Other members of the crew contributed in different ways. They steered the ordered course, tended the sails, turned the sandglass, cast the log line, and recorded depths. Navigation was supported by many hands, even when only one person stood beside the rail with an instrument. Together, their work helped to give the vessel a place upon the chart. Yet latitude supplied only one part of that place. It revealed how far north or south the vessel was. It did not reveal how far east or west it had traveled. Two ships could share the same latitude while being separated by the breadth of an ocean. That east and west position was longitude, and measuring Polaris could not disclose it. For now, the navigator compares the observed latitude with the position estimated from the ship's course and speed. The two agree closely enough to be reassuring, though neither is treated as perfect. Under the shelter of a shaded lantern, a measured figure is entered into the notebook. The page carries the date, the estimated course, and a few restrained remarks about the wind and sea. The ink settles into the paper. Then the book is closed and the navigator looks north once more. Polaris continues its small circle around the unseen pole. The surrounding constellations turn slowly with it, while the vessel moves over long, dark swells. Timber creaks softly, water passes along the hull. Above it all, the cool northern star remains nearly steady, offering direction and latitude, but not the vessel's complete position. After a time, the eastern sky begins to lose a little of its darkness. The stars nearest the horizon grow faint. A cool gray line spreads above the water, announcing another celestial guide, brighter, warmer, and best observed with care. Chapter 9. Sunlight, Noon, and the Sextant. The eastern sky brightens by degrees. Gray becomes pearl, pearl becomes pale gold, and the last stars disappear into the growing day. Along the deck, ropes and spars take on their familiar shapes. The sea changes as well. It is no longer a dark, nearly featureless plain, but a wide field of low blue ridges, each one touched by the morning light. The navigator has already made use of the stars. Now another kind of observation can begin. The sun is an especially useful guide, because its movement across the sky follows a dependable daily pattern. It rises in the east, travels in a long arc, and sets in the west, though the exact places of sunrise and sunset change with the seasons and with the observer's latitude. Its path is shaped by the tilt of Earth's axis. In summer it may climb high and remain above the horizon for many hours. In winter, it follows a lower and shorter course. These changes were not merely inconveniences to be guessed around. They could be observed, calculated, and recorded. Astronomers prepared tables showing where the sun would appear on each day of the year. Collections of such information, called nautical almanacs, allowed a navigator to connect an observation made at sea with the known motions of the heavens. The vessel continues onward beneath a clearing sky. Breakfast smoke drifts briefly from the galley before the breeze carries it away. Above the mast, a few high clouds move slowly westward. The sun is still low enough to cast long shadows across the planks, but it is steadily climbing. As it rises, the navigator considers the coming noon sight. Local noon does not simply mean 12 o'clock by a watch. It is the moment when the sun crosses the observer's meridian, an imaginary north to south line passing through the sky and directly overhead. Around that time, the sun reaches its greatest altitude of the day. In navigation, altitude means the angular height of a celestial body above the horizon. A star resting on the horizon has an altitude of about 0 degrees. A body directly overhead has an altitude of 90 degrees. Between those two limits lies every rising star, every planet, and the sun as it moves through the daylight sky. By measuring the sun's altitude near local noon, and then consulting the date and the astronomical tables, a navigator can estimate latitude. The principle is related to the one used with Polaris, but the calculation requires another piece of information. The sun's apparent position north or south of Earth's equator changes throughout the year. This position is called declination. Declination is rather like latitude projected onto the sky. During certain seasons, the sun is north of the equator. During others, it is south. The almanac provides the appropriate declination for the day, while the observing instrument provides the altitude. And with attention to whether the sun and the observer lie north or south of the equator, the navigator can determine the vessel's latitude. Long before the sextant became common, sailors used simpler instruments to measure such angles. One was the cross staff. Its observer looked along a long wooden staff, while sliding a shorter crosspiece forward or backward. One end of the crosspiece was aligned with the horizon, and the other with the celestial body. The position of the crosspiece then gave the angle. The method could work, but observing the bright sun in this way was uncomfortable and potentially harmful to the eyes. Later instruments, including the backstaff, allowed the navigator to face away from the sun and use its shadow instead. Each new design represented an effort to make celestial measurements safer, steadier, and more practical on the moving deck of a ship. During the 18th century, reflecting instruments came into wider use. One early form was the octant, named for the 1/8 circle arc built into its frame. Through the useful geometry of reflected light, An octant could measure an angle twice as large as the arc itself. The later sextant had an arc equal to 1/6 of a circle. It could measure still greater angles, and became one of the best-known instruments of traditional ocean navigation. The sextant carried aboard this vessel rests in a fitted wooden case. When the lid is opened, its frame appears delicate, balanced, and purposeful. There is an arc marked in degrees, a movable arm, a small telescope, mirrors, and darkened glass shades for observing the sun safely. Its operation depends on double reflection. One mirror moves with the instrument's arm, another is fixed near the telescope and is partly transparent. This arrangement allows the observer to see the horizon directly through one portion, while seeing the reflected sun through another. By moving the arm, the navigator makes the sun's reflected image descend toward the visible horizon. When the lower edge of the sun appears to rest upon that line, the angle can be read from the graduated arc. For a moment, the instrument seems to bring the sky and sea together. Yet the act requires patience. The ship rises and settles with the swell, so the horizon moves within the telescope. The sun's image moves as well. The observer gently rocks the sextant from side to side, causing the reflected sun to trace a small arc. At the lowest point of that arc, its edge just touches the horizon. The navigator adjusts the fine screw, waits through another easy roll of the vessel, and checks once more. Dark shades protect the eye from the sun's brilliance. No careful observer looks directly at the sun without them. As noon approaches, measurements are made at intervals. The sun climbs more slowly now. Each reading is a little higher than the one before, until at length the sun appears to pause near the top of its arc. Afterward, the measured altitude begins to decrease. The greatest reading marks local noon closely enough for the navigator's purpose. The number taken directly from the sextant is not yet the final answer. A few small corrections may be needed. The observer's eye stands above sea level, making the visible horizon appear slightly lower than a perfectly level horizon. This effect is called dip. Earth's atmosphere also bends light, especially near the horizon, producing an effect called refraction. The sun has a visible disk rather than appearing as a single point, so the navigator must note whether its upper or lower edge was brought to the horizon. The sextant itself may also have a small instrumental error, checked beforehand and allowed for in the calculation. None of these corrections is very large in an ordinary noon sight, but together they matter. Navigation becomes more dependable when small influences are acknowledged, rather than ignored. At a sheltered place near the companionway, or below deck, where the papers will not be disturbed by wind, the navigator opens the almanac and begins working through the figures. The page is filled with orderly columns. The corrected altitude reveals the sun's angular distance from the point directly overhead. That distance, combined with the sun's declination for the day, gives the vessel's latitude. The result is entered in the notebook, beside the morning's course and estimated position. It agrees reasonably well with the reckoning carried forward from compass direction, speed, and elapsed time. The agreement does not prove that every number is exact. The horizon may have been slightly hazy. The vessel may have drifted under the influence of wind or current. The observation itself may contain a modest error. Yet when separate methods lead toward much the same answer, confidence grows. Each method supports the others, not by offering perfection, but by narrowing uncertainty. For centuries, the noon sight became a steady rhythm of life at sea. It divided one navigational day from the next. Officers might arrange their daily records around it, while the crew came to recognize the familiar appearance of instruments, almanacs, and notebooks near midday. Above them the sun reaches its highest place. For a little while, shadows are short upon the deck. Light glances from brass fittings and lies warmly across the open pages. Then the sun begins its slow descent toward evening. A careful solar altitude can answer the north to south question with useful accuracy. It can provide latitude, yet the east to west question remains more difficult. Latitude alone cannot reveal a vessel's complete position. Two ships separated by a great distance east and west might still share the same latitude. To find longitude, the navigator needs more than an angle in the sky. The navigator also needs dependable knowledge of time somewhere else on Earth, so that local time aboard the vessel can be compared with the time at a chosen distant meridian. The sextant is wiped, checked, and returned to its fitted case. Its lid closes softly. The almanac remains open for a while. its columns of figures resting in the warm moonlight. Nearby, a watch ticks steadily, preserving the hours of a distant meridian as the vessel continues across the sea.